Hi everyone, I'm Nachiket from Eleno. Today let's talk about one of the most fascinating areas in material modeling, which is hyperelastic materials and how we model them in LS-DYNA. It's really important conversation for us to have. Whenever we deal with materials like rubber, gaskets, tires or even human tissues, we notice one thing: they stretch a lot and they return back to their original shape. These are non-linear elastic materials and their behavior cannot be explained by a simple Hooke's law. That's a fact. And we have to understand that instead of defining a constant modulus, we define how the material stores and releases energy during deformation. That's important. That's the essence of hyperelasticity. The stress in the material is derived from its strain energy density function. In simple words, when you stretch a rubber band, the software is actually calculating the stored energy, and from that it derives the stress. That's crucial, right? Let's see how LS-DYNA handles it. Okay, in LS-DYNA we have several powerful material models for hyperelasticity. Some of the most commonly used are MAT 027, that is Muni-Rivlin rubber, very common. MAT 077, which is Ogden rubber, and MAT hyperelastic rubber, which is MAT 181. And then you have MAT 092 Blatzko foam and other bits. So there are multiple models. Each one uses a different strain energy function, like Muni-Rivlin, Neo, Hookean or Ogden. So the material behavior is different in large deformations. That's what we have established. But how do we get the parameters for these models? We need experimental test data from uniaxial tension, biaxial tensions and planar shear stresses, shear tests. The data from these tests is used to fit the parameters in our model. Okay, in LS-DYNA you can use LS-Prepost, which is a free tool to perform its fitting and generating coefficients for MAT 077 or MAT 181. Once the model is ready, the next important step is validation, because you have defined some parameters, you have to validate them. We simulate real life tests, for example a rubber bushing compression test or a tire inflation. If the simulated force displacement curve matches the experimental one, that means our hyperelastic model is accurate and ready to use. This is particularly important. Okay, so there are some mistakes which engineers can make, okay, using linear elastic models for rubbers. Ignoring incompressibility, Poisson's ratio close to 0.5, applying incorrect boundary conditions during large deformation. So these are some of the mistakes. Always remember, hyperelastic models are sensitive to both test data and boundary setup. Okay, so you can have a correct test data, but if your boundary conditions are wrong, it's not going to perform well. So to summarize, hyperelastic materials help us model nonlinear elastic behavior that's essential for simulating rubbers, foam and biological tissues. LS-DYNA provides robust and physics-based tools to handle these materials accurately. If you are working in crash, durability or even biomechanics field, mastering hyperelasticity modeling will be superior edge in your career path. Okay, I hope this gave you a clear understanding of how we model hyperelastic materials in LS-DYNA. Do follow Eleno for more insights on design using CAE and to build a sustainable physics-based engineering career. We are available on LinkedIn, YouTube, Instagram, Facebook. Make sure you subscribe. Make sure you are connecting with me. Myself Nachiket Phadke, signing off. Bye guys.